Greetings to all of you. In the last lecture, we have discussed the magnetic circuits, some example problems, right. Now, in this lecture, we will discuss the magnetic circuits with multiple winding excitations and permanent magnets. Okay. First, we will see the magnetic circuits with AC excitation. I have considered the same magnetic circuit what we have discussed in the last lecture. Here we can see AC supply we are giving at the electrical side, flow variable is current and effort will be voltage, AC voltage, and both voltage and current are sinusoidal quantities displaced by 90 degrees, and current will be lagging. We can see the current and voltage waveforms here, and analysis and approach for analyzing this circuit, everything is same. Only while calculating the magnetic fields, we have to consider the RMS quantities. B equals to mu n I, right, where we have to calculate the RMS quantity instead of peak or instead of average. So, B equals to mu n I into RMS quantity, and remaining things will be same. Here RMS quantity we can calculate it V by impedance, based on that we can calculate. Next, we will see the magnetic circuits with multiple windings. Let us consider the magnetic circuit having a core permeability mu and length of the core is LC, and the windings, one winding is placed at this place or in the window 1, and other winding is placed in the window 2. The effort and flow variables in coils V1 and I1 with respect to the first coil, and V2 and I2 is with respect to the coil 2. Apply a thumb rule and find the magnetic flux, okay, or magnetic fields, same way whatever we have done as of now. Apply a thumb rule. In both coils, the flux is in this direction with respect to the thumb. Fingers I am representing with current, B fields with thumb. We can see here current is entering this side, going in and coming out in this fashion, then the flux lines are in this direction. B fields are flux lines. Flux lines we can represent it with flux. Flow variable representation will be d phi by dt. Okay. To represent the flux lines only, we can go with flux or d phi by dt, but flow variable is d phi 1 by dt, and flux with respect to the coil is this one phi 2, this is phi 1. Okay. The flux with respect to the each coil, the flux linking with respect to the each coil consists of different components. The phi 1 is the flux which is linking or which is associated with the coil 1, consists of the magnetizing flux and leakage flux component. The leakage flux component is nothing but the flux which is generated with respect to the current in coil 1, and it is not linking with any circuit, any magnetic circuit or any coil, that is nothing but phi L1 leakage flux. Okay. Next, phi M is the magnetizing component. It has two components. One is with respect to the coil 1, that is phi M1, one is with respect to the coil 2. If we will take separately coil, one coil I am drawing here, this is phi M1, phi M2 is coming this side, and the leakage flux with respect to the coil is phi L1. The phi m1 is the magnetizing flux component, the flux which is generated with respect to the current 1 and it is linking with respect to the all magnetic circuit that is flowing through the core and linking with the coil 2 also. I will draw with some different color. Okay. We can see here the phi m1 is linking with coil 1 and coil 2 and flowing through the complete core. This is phi m1. Similarly, phi m2 is the current which is generated with respect to the coil 2 current and it is linking with all coils and as well as complete core. This is generated with respect to the current I2 and phi m1 is generated by the current in coil 1 is that is phi m1. So, the flux component which is linking with respect to the coil 1 we can write it phi L1 plus phi m1 plus phi m2. This is the leakage flux only linking with the coil 1, it is not linking with core or coil 2. Phi m1 is the magnetizing flux generated with respect to the current I1 and linking with the rest of the circuit core and coil both coils, and phi m2 is generated with respect to the current I2 and linking with the both coils as well as core. Phi 2 again we can write it as phi L2, the leakage flux associated with coil 2. This is phi L2. Then phi m1 plus phi m2. These are just flux representations, not the flow variables. Flow variable is always d phi 1 and d phi 2 by dt. Now, we will apply the same analysis to visualize the or to analyze the circuit. Second step, we have to draw the equivalent circuit, right. The MMF with respect to the coil 1 and MMF with respect to the coil 2 and the capacitances. I am considering this capacitance or this magnetic length path is Ly and this magnetic length path also Ly and middle portion magnetic length path is Lx, and there will be flux lines here also the flux lines will be there. Some flux lines will flow here also. This is Ly, Ly and this region yellow color region is Lx, length of that magnetic path. So, I can draw the equivalent circuit in this fashion. This is capacitance with respect to the Lx portion and then the capacitance with respect to the magnetic length path Ly. I am showing here, this is CMY and CMY this side also. The flow variable here is d phi 1 by dt, here d phi 2 by dt. Now, we have to analyze this circuit. With respect to the KVL, MMF should be equals to from the loop 1. This is loop 1 and loop 2. In loop 1, MMF is equals to MMF with respect to the CMY and CMX, right. So, V CMY is nothing but 1 by C M y integral I dt, right. I is nothing but d phi 1 by dt into dt plus 1 by Cm x integral of d phi 1 by dt minus d phi 2 by dt into dt. If we will solve this thing, then we can get 1 by Cmy into flux phi 1, 1 by Cmx into phi 1 minus phi 2, difference in both flux values. This is the MMF equation with respect to the capacitances. Like this we have to make the equivalent circuit and we have to realize in this fashion. If we are representing with resistances in terms of reluctances, mathematically you may get same equation, but it is wrong with respect to the power balance or energy conservation, and reluctance is not a dissipating element. Conventionally you will see in most of literatures in this fashion. Here flux phi 1 and here flux phi 2, like this you will see, but it is wrong. We have to use this type of circuit only. This type of circuit we should not use, but you may end up with same equation, but it is technically and conceptual wise we should not represent in this fashion. And MMF in terms of reluctances, if you will write phi 1 into Ry plus phi 1 minus phi 2 into Rx. Next, KVL with respect to the loop 2, if we will apply from in this loop. For loop 2, MMF is equals to Vcm x plus Vcm y. Here 1 by Cm x integral of d phi 1 by dt minus d phi 2 should come, d phi 1 by dt plus 1 by Cm y integral of d phi 2 by dt into dt. So, final equation will come MMF with respect to the coil 2 N2 I2 is equals to, this is N1 I1, MMF 1 we can call it, this is MMF 2, N2 I2 is equals to 1 by Cm x into phi 2 minus phi 1, we will get it 1 by Cm y capacitance into phi 2. In terms of reluctance manner, you can represent phi 1 minus phi 2 into Rx plus, sorry, phi 2 minus phi 1 it is, then phi 2 into Ry. Then next step, Faraday's laws we have to apply and we have to find the inductance relation. As per the Faraday's law, L into I is equals to N into phi. So, phi 1 is equals to L1 into I1, that is N1 into phi 1 flux. Number of turns with respect to the coil 1 and flux with respect to the coil 1, or flux is linking with the coil 1 is the accurate word, that is phi L1 plus phi M1 plus phi M2. These are the fluxes linking with respect to the coil 1. Phi L1 if we will replace in terms of MMF and reluctance, then N1 into I1 divided by R L1, reluctance with respect to the leakage flux magnetic path, N1 into I1 divided by Rm. This is reluctance with respect to the magnetic flux loop in a core, N2 I2 divided by Rm. So, we will see the final equation N1 square into I1 by RL1 plus N1 square into I1 divided by Rm plus N1 N2 into I by R reluctance with respect to the core. The first two terms represent the self inductance terms. N square by reluctance it is coming, right, because we are seeing the flux linkages L1 into I1. If required, we can reframe the equation or rearrange the terms RL1 plus N1 square by Rm into I1 plus N1 N2 by Rm into I2, this is I2, L1 into I1 flux linkages with respect to coil 1. So, these first two terms represent the self inductance terms. We can call it as L11, that is equals to LLS plus LMS, leakage inductance plus magnetizing inductance. This is mutual term, mutual inductance. We can write it L11 into I1 plus L12 into I2. This is L1 into I1 flux linkage with respect to the coil 1. Similarly, flux linkage with respect to the coil 2 L2 I2 is equals to L22 into I2 plus L21 into I1. These are the inductance equations with respect to the flux linkages. The performance curves will not change with respect to the other circuits what we have discussed, only magnitudes will vary. This is B versus H waveform in a linear zone, it will be mu will be constant, we will see the linear characteristics and there is no saturation. After that we will see the saturation where mu value is almost is equals to 0 and B will not change and only H will vary. And inductance versus current waveforms also same, it will vary in this fashion, inductance versus current, and flux linkage psi versus current, it will vary same as the BH curve in a linear region, it will be constant with a slope L, or we can represent in terms of mu also. In a non-linear region the core will saturate and you will see the flux linkage versus current waveform in this fashion where mu equals to 0. This is the analysis with respect to the multiple winding excitations. Next we will discuss with respect to the permanent magnets, magnetic circuits with permanent magnets. Let us consider a magnetic circuit with permanent magnet. The permanent magnet length is Lm and area is Am. Area of the magnet is Am and there is a core portion as well as air gap portion. This is the core portion. This core having a permeability of mu, it will be very high and length of air gap is Lg, and because of the permanent magnet you will see the flux lines in this fashion as per our Oersted principles. The permanent magnet flux lines we can see in the core, and flow variable here also d phi by dt, but there is no effort variable with respect to the winding, but here effort variable is Fm, that is a permanent magnet. Source is Fm, mmf with respect to the permanent magnet, and d phi by dt is the flow variable with respect to the effect Fm. Generally the permanent magnets consist of wider BH loops. We have discussed while discussing the magnetic materials. These are the BH curves for magnetic materials, sorry, permanent magnets. It has higher value of retentivity B value and cohesivity H value we can see here for permanent magnets. The examples for permanent magnets: alnico, samarium cobalt, and neodymium magnets and strontium ferrites, etc. We can consider it as examples of permanent magnets, and the analysis with respect to the permanent magnets is same as the magnetic circuits what we have discussed as of now. First step, we have to apply the Oersted principle, that already we have seen, and flux direction also we have identified. Now we have to calculate the, or we have to realize the equivalent circuit of this magnetic circuit. Here the effort variable is Fm, like mmf with respect to the permanent magnet, and the capacitance with respect to the core in this portion, and then this portion also, and air gap will be in this region. So capacitance Cm with respect to the core, and with respect to the air gap Cmg air gap, then another capacitance will come at the core side, that is Cm. So here flow variable again d phi by dt. The permanent magnet flux is constant. With respect to that, we can say that we can consider here flux. It depends upon the how much magnetic fields we have to store at the air gap. Depends upon that, flow will be there. d phi by dt will be there. Once it will fully charge, there is no d phi by dt. Step 3, we will apply the Ampere's law. Integral h dot dl is equals to n into I. Here there is no n into I term with respect to the winding, it is equals to 0, and permanent magnet one is Hm into Lm. With respect to the core, Hc into Lc, and with respect to the air gap, Hg into Lg. This is the MMF equation as per the Ampere's law. From here, Hg, the magnetic field intensity with respect to the air gap, is equals to minus of Hc Lc plus Hm Lm divided by Lg. This is equation number 1. If we will consider the core has the permeability value is very high, and there is no MMF required to magnetize the core, or very less magnitude of MMF is required, okay, to magnetize the core. So we can neglect this term, and Hg is equals to minus Hm into Lm by Lg. Why we are neglecting this term means mu value is very high, and the magnetization required for the core is with respect to the MMF is negligible or very small. Because of that reason I neglected this thing. This is equation number 2. Now the flux relations we will see. The flux in the core as well as flux associated with the magnet, flux in the air gap, everything is same. So, phi c is equals to phi m is equals to phi g. So, phi m is with respect to the magnet, B m magnetic flux density into area of the magnet. Phi g is nothing but flux density with respect to the air gap and area with respect to the air gap. From here we can get the B m is equals to B g by A g divided by A m. This is equation number 3, and we can write the relations B m and B g values with respect to the mu and h. This is mu into h m and this is mu g into h g. This thing we have to find from the BH curve of magnetic permanent magnet material. Bg is equals to mu g into hg. Okay. If we will substitute that term in the equation number 3, then we will see mu g into hg into Ag divided by Am. Here hg value we have to get it from equation 2. Substitute here equation number 2, then flux density with respect to the magnet is equals to mu g into minus hm into Lm divided by length of air gap into Ag by Am. If we will rearrange the terms, mu g or mu naught into Lm into Ag by Am and Lg term also there into Hm. This is the equation representing the Bm and Hm, flux density and flux intensity with respect to the magnet. So, if we will draw a line with respect to the BH curve of the permanent magnet, only second quadrant I am considering, it will be in this fashion, right, for permanent magnet wider BH loop. If we will draw a load line or with respect to the equation number 4, we will see in this fashion. This is the line equation with respect to the fourth equation. The cross sectional point is nothing but operating point. We have to design the magnet with respect to this operating point, and this point will give the maximum energy product. This minus represent the operation or operating point with respect to the second quadrant. Next we will see how much magnitude of or how much volume is required to establish the flux density Bg in the air gap. How much volume of the magnet is required to establish the required flux density at the air gap. So, volume of the magnet is equals to area of the magnet into length of the magnet. Area of the magnet we have to get it from the flux relation. Bm Am is equals to Bg into Ag. From there Am is equals to flux density at the air gap divided by flux density of the magnet into Ag. Lm we have to get it from the Ampere's law, that is equation number 2, Hm Lm by, if requires we require Lm, right. So, Hg Lg by Hm we can write it. Then rearrange these terms and substitute Bg value is equals to mu G into H G. Then finally we will see Bg square into Ag Lg divided by mu naught into Bm into Hm, the magnetic flux density with respect to the magnet and flux intensity with respect to the magnet. This is flux density square divided by mu naught into Bm Hm into Ag into Lg product. We can represent it as a volume of the air gap, that is Vg. This side Vm is there. This equation tells that in order to establish the magnetic flux Bg at the air gap, we require a magnet of volume Vm, and the Bm and Hm value should be maximum. Next we will see how to solve the magnetic circuits with magnetic circuit problems with respect to the permanent magnets and windings inside windings in the magnetic circuit. Let us consider this is a magnet, and here we have electric side coil to produce the required MMF V and number of turns N, and flow variable with respect to the coil is d phi by dt, and flux if we will talk, that is phi, and this permanent magnet length is Lm and area is Am. The approach to solve the problems associated with magnetic circuits, single excited and permanent magnets or permanent magnets with air gap, approach will be same. With respect to the different parts of or different lengths of magnetic paths, we have to identify the regions where the flux densities values may change, but flux is same in the core. Flux densities will change as per the cross sectional areas of that particular region. I am marking the locations with respect to different parts of the core, this red color one, and then we have to mark it. This is 1, 2, 3, 4, 5, this 6, and magnet portion 1 is 7. Draw the equivalent circuit and solve the problem similar to the network theory concept. Here MMF with respect to the coil is N1 into I1 or N into I simply, and the capacitance with respect to the region 1 is C1 and capacitance with respect to the region 2 is C2, then C3 with so we represent all the reluctance paths in terms of capacitances where the energy is stored, C6, C5, and the permanent magnet MMF we can represent it here N Fm, there is no number of turns Fm, and this side flow variable is d phi 1 by dt, this side we have to consider d phi by dt with respect to the magnet and analyze the circuit. So, with this I am concluding this lecture. In this lecture we have discussed the magnetic circuits with multiple windings, magnetic circuits with permanent magnets and the respective equivalent circuits and analysis. Thank you.